So, have you ever stood at the base of a towering, glass-clad skyscraper, craned your neck all the way back, and just wondered, how on earth does this thing actually stay upright? I mean, we look at these absolute giants of modern construction piercing the clouds, and they seem so, well, permanent, right? So invincible. But as we know, our planet is incredibly active, and the ground beneath these engineering marvels is far from entirely stable. So today, in this explainer, we're going to demystify the incredible engineering that keeps these enormous structures safely standing, even when the Earth itself literally throws a tantrum. We're going to break down the basic engineering and structural model and the brilliant design choices that protect millions of lives every single day. Let's get into it. It really is a massive paradox when you think about it. On one hand, you've got the completely unpredictable, terrifying power of seismic activity, nature shaking the very crust of the Earth with just unimaginable energy. And then, on the other hand, you have a 100-story building. From the outside, it looks incredibly precarious, right? Kind of like a giant glass needle just waiting to tip over. To the untrained eye, a skyscraper seems like absolutely the worst place you could possibly be during a tremor. But here's the crazy part. Modern skyscrapers are actually some of the safest places you could possibly hide. To understand how that's even possible, we have to look past those beautiful glass facades and dive deep into the building's basic engineering and structural model. Okay, let's dive into this. Here is our roadmap for today. 1. The forces of earthquakes. 2. Basic structural engineering models. 3. Primary engineering innovations. And 4. Materials for ductile frames. Section 1. The forces of earthquakes.
All right, before we can understand the defense, we really have to understand the attack. When a massive tectonic shift happens, the ground doesn't just rumble. It unleashes this chaotic, multi-directional assault of kinetic energy onto literally everything resting above it. Now, while the ground certainly moves up and down during a seismic event, it's really the side-to-side motion that keeps engineers awake at night. We call these lateral forces. That's the sideways, completely unpredictable shaking that aggressively threatens a building's structural integrity. Think about a tall stack of blocks. If you tap the table underneath it from the bottom up, the stack might just bounce a little bit. But if you quickly jerk that table left and right, that stack is going to almost instantly shear apart and collapse. That violent lateral movement is absolutely the most catastrophic basic engineering challenge when designing a skyscraper.
Section 2. Basic structural engineering models. So, the crucial point is how we actually handle that lateral force. For a long time, the old basic engineering model relied on creating rigid structures. And hey, the logic seems sound at the time. If the Earth is going to hit the building with force, we just need to make the building as stiff and immovable as possible, right? Well, there's a fatal flaw there. Think of a dry, rigid winter twig. If you apply force to it, it doesn't give, it just snaps. And that's exactly what rigid buildings do under immense lateral stress. They crack and they fail. Now, contrast that with the modern model, flexible structures. Instead of fighting the energy, modern basic engineering models are designed to actually absorb it. Picture a green, living willow branch in a violent windstorm. It bows, it bends, it whips around. But because it's flexible, it safely survives the storm without snapping. Section 3. Primary engineering innovations.
To make a massive building, we're talking something made of thousands of tons of metal and concrete, behave like that willow branch rather than a dry twig. Modern basic engineering relies on 3 primary structural innovations. Together, they create a defensive mechanical system. We have base isolators at the very bottom, cross-bracing throughout the skeleton, and tuned mass dampers near the roof. Working together, these 3 systems manage, dissipate, and counter the violent energy injected into the building by an earthquake.
Let's move to the foundation and see exactly how this builds up, starting at ground zero with base isolators. Imagine putting a skyscraper on giant, heavy-duty roller skates. When a quake hits the foundation, these isolators act as massive shock absorbers. They effectively decouple the building from the violently shaking earth. So as the ground aggressively jerks left and right, the flexible isolators allow the building above to just gently glide horizontally. It dramatically reduces the amount of lateral force that ever even makes its way up into the structure. Even with those isolators, some energy is inevitably going to travel up the building and cause it to sway. And this is where we look at the engineering magic happening at the very top of the structure. Tuned mass dampers are massive, multi-ton counterweights suspended near the roof of the skyscraper. When an earthquake pushes the building to the right, this giant internal pendulum swings back to the left. It literally pushes against the earthquake's momentum. By swaying out of phase with the building, the mass damper neutralizes that violent swing and prevents the entire skyscraper from whipping back and forth out of control.
Section 4. Materials for ductile frames. And this brilliantly illustrates our next point. because you can have the absolute best base isolators and mass dampers in the world, but if the bones of your building, the cross-bracing and the vertical columns are made of the wrong material, the entire flexible model will just fail. To understand material selection, you need to know one absolutely crucial concept, and that is ductility. Ductility is basically the ability of a material to deform under stress without fracturing. It means that when you pull, twist, or bend it with extreme force, it's going to yield and stretch. It absorbs the energy rather than just shattering. So if you want a flexible building, you absolutely require high ductility.
Now, what's really interesting to consider is how different materials stack up. Take standard concrete, for example. It has high compressive strength, meaning it can hold a ton of weight, but it's incredibly brittle. It has a really low ductility. Under lateral earthquake forces, it acts exactly like that dried twig we talked about earlier. It just cracks and snaps. But then consider reinforced steel. Steel is highly ductile. It's really the ultimate secret weapon for modern architectural frames because it can bend, stretch, and absorb massive amounts of energy without actually losing its overall structural integrity. By building a skyscraper skeleton out of highly ductile reinforced steel, engineers ensure the entire basic engineering model functions as planned, flexing right along with the earthquake's rhythm.
So when you combine a highly ductile, reinforced steel frame with those base isolators and tuned mass dampers, you get the ultimate result. You don't just have a tall building anymore. You have a highly advanced, responsive mechanical system. This basic engineering and structural model neutralizes terrifying kinetic force. It allows cities in highly active seismic zones to safely build upward, protecting millions of lives in the process. It's honestly a beautiful symphony of physics and material science, all working perfectly together in real time. Which leaves us with this final thought. We've mastered the basic engineering and the underlying models of ductility, isolation, and dampening. But as our global cities continue to grow even taller, and as tectonic forces remain as powerful and unpredictable as ever, what's the next frontier in structural engineering? Are we going to see buildings made of completely new, smart materials that can actually change their stiffness on command? Or maybe structures that actively push back against the Earth using artificial intelligence? The modern built environment is just endlessly fascinating, and the quest to conquer the forces of nature is clearly far from over. Thanks so much for joining me on this explainer, and hey, keep looking up.